Doctor, you can start now.
Appreciate that. Like the metallic medicines or mineral medicines or DESA medicines can be administered in lesser doses, and that are only needed in lesser doses, and there is no palatable issues as well, and faster action, rapid systemic absorption as well as system action can be brought out by the metallic and mineral medicine. So that is explained in the sloka. Alpamatra upyogitvad arijeye aprasangadaha kshipramarogyadayitvad aushadebhyo atigo rasaha. So these are the superior qualities of rasaushadis. So the metals and minerals are converted into bhasmas through a process known as bhasmigarana or marana. So through this process, the metals and minerals are converted into sub finer particles, or converted into finer particles, and the toxic effects of the metals and minerals can be reduced through the processes, and new qualities can be incorporated in the metal and mineral medicines. So all these processes will remove the unwanted properties as well as add new qualities to the medicines. So these are the importance of bhasmas. So after preparing the bhasmas, we need to analyze the bhasma for its quality as well as purity. So in Ayurveda, these bhasma analysis or bhasma tests are known as bhasma parikshas. So these bhasma parikshas have detailedly explained in Rasa Shastra textbooks. So uh, in Bhasma Parikshas, so the Bhasma Parikshas can be broadly classified into two. That is traditional analytical tests and current analytical tests. So current analytical test is the modern analytical test using modern techniques, modern equipments. But traditional analytical tests are explained as Bhasma Parikshas in the context of Bhasmigarana. So the traditional analytical test is again divided into physical test and chemical test. These we were covered in the chapter of Marana as well as Bhasmigarana aspects in the Rasa Shastra. So the traditional analytical tests are divided into two, that is physical test and chemical test. And physical test will include Mridaloha or Rekha Purnatva, Varidaratva, Hamsa Varidaratva or Unnama, Nirdhumatva, Gatarasatva, Nischandratva, Mridutva, Slakshnatva, Anjana Sadrisha, Sukshmatva. So these are the physical tests of Bhasma. And chemical tests, I'm not going to explain these things since I have taken and I have elaborated these tests in the Marana aspects. So Marana, Shodhana, Marana, Amrigarana chapter, I have detailedly explained all these tests. Okay. So the chemical tests will have Apunarbhava and Nirutta. So these are the traditional aspects of Bhasma quality control analysis, quality check. Okay. Uh, Coming to the current analytical tests, there are four, these can be divided into four types, that is organoleptic evaluation, physical evaluation, chemical analysis, instrumental analysis. Okay. So nowadays, with the development of science and technology, we could test and analyze the prepared bhasma through modern parameters. So the traditional tests are not sufficient to establish the genuinity of the bhasma. Though we uh, first we will test or analyze the bhasma through traditional analytical procedures, then only we will go for a current analytical test. And these traditional analytical tests are needed in each step of the Marana process also. So in each step of Shodhana or Marana process, we cannot go for the current analytical tests, which are costlier than the traditional analytical tests. The traditional analytical tests are very easy to perform. So that is why it is being widely accepted for the preparation, for the stepwise preparation of a bhasma. So after each marana process, after each puda, we will check for the varidaratva and rekha purnatva of a bhasma, whether the bhasma is attained, the rekha purnatva or varidaratva. Then if we have obtained the rekha purnatva and varidaratva, we will move on to the current analytical test, that is divided into 4. That is organoleptic evaluation, physical evaluation, chemical analysis, instrumental analysis. So first we will go with the organoleptic evaluation. So in the organoleptic evaluation, which is again divided into color, odor, taste, and touch. So these 4 parameters are checked in the organoleptic evaluation. So the color, we know for each type of basma, there are specific colors have been mentioned in the traditional textbook. So we will continue doing the puta, or we will continue doing the basmegarana process up until we get the optimum color of the basma. For example, Tamra Basma and Rajata Basmas are black in color. Swarna is Champaka Varna. Kamsya is Dusara Varna. Naga Basma is Paravada Varna, ash color. And Vanga Basma is Shubhra, white color. And Tikshna Loha is Jambu Falobama. And Abhragam to Ishtigabham. So Ishtigabha Varna. Kasisam is Gaidiga Varna. So likewise, for all the metals and minerals explained in the Shastra, peculiar specific colors I've also mentioned. So we have to check for the color to finalize, to identify the or to determine the final stage of Basmegarana. Okay. Next is the order. So generally the well prepared Basma will not have any specific order. Okay. And for when it comes to taste, the basma generally, when it is prepared properly, will not have a specific taste also. In certain basma, it has been specifically mentioned as niramlada. That is, it should not taste sour. So in Kasisa basma nirmana, Yavad Basmam Niramlada. So, Kasisam Nimbu Nirena Mardetwata Chakliga, Shushka Karya Sampudasta, Dasha Prasta Vanopalegi, Punaha Pudadeyam Yavad Basmam Niramlada. So, when it attains, we have to continue the process of Basmigana till it loses the sour taste. So, that is the taste. That is the organoleptic evaluation of taste. And touch, we can say that slakshnatva, murdutva, and these can be identified as touch. That is, the touch, the basma, properly prepared basma has to be smooth to touch. So that is the smooth and soft to touch. So that is the peculiarity of touch. So these are the 4 analytical parameters which are checked in the organoleptic evaluation. Okay. So the first one is organoleptic evaluation, that is completed. Second one is physical evaluation. So let's go to physical evaluation. So physical evaluation comprises of loss on drying at 105 degrees Celsius, ash value, solubility, specific gravity at 25 degrees Celsius, and pH. So these are the physical evaluation which are done to check the quality of the basma. So, coming to the loss on drying at 105 degrees Celsius. As the term indicates, it is loss on drying, the loss of moisture on drying of the sample. So, the sample is dried and the loss of moisture, the loss of moisture is identified and calculated to find out the loss on drying of the sample, or LOD of the sample at 105 degrees Celsius. So it is a measure of amount of water and volatile matters in a sample when the sample is dried at 105 degrees Celsius. So the process is very simple. So the first weigh the sample, and so for this purpose, loss on drying, we need only weighing balance. We need only 3 apparatus, that is weighing balance, 1 desiccator, and a ceramic crucible for the determination of loss on drying, LOD. So first weigh the sample and dry the sample at 105 degrees Celsius in hot air oven, and take out the sample and keep it in the desiccator to cool down. So why we are keeping it in desiccator? Because to cool down in a natural atmospheric temperature and to avoid absorption of moisture from the atmosphere. So So after it is completely cooled down, we have to take the sample and measure it, and we have to note the sample also. So, we have to note the weight of the sample. So we need to repeat the process until the weight of the sample remains same. So that means that there is no more moisture is left in the sample. So we have to note down that weight also, and then we have to do a calculation. After that, we will do the it is basically the loss on the raw material sample weight and the loss on drying sample weight of the weight after the drying process. So a calculation is done to find out the percentage of loss on drying. Okay. So the LOD. So how much of the weight of the sample? Based on that, we can determine the moisture content which was present in that sample. So loss on drying is very important when it comes to Basma Parisha, because as you know, the moisture will absorb the moisture is a great place to for a fungal growth. So loss on drying is a very important parameter in checking in quality control of Basma. Okay, so so this is the apparatus that are needed for loss on drying, that is weighing balance, desiccator, and a ceramic crucible for the purpose of keeping the sample. Okay, so nowadays we have like fully automated machineries for the identification of loss on drying. So this is one of such a automated machine in which you can just take your empty sample pan, load the testing sample onto the sample pan, and press start and see your results. That is the manual for this fully automated machine for a loss on drying. So nowadays we have this kind of fully automated machines for the identification of loss on drying. Okay. Next one is ash value. So we know that ash value is to determine the quality as well as the purity of the basma. So we know that after identification of the ash value, we could able to find out the percentage of the silica in the basma. So it shows the impurity. If the percentage of the silica is more, it shows the impurity of the basma. So to test the purity as well as the quality of the basma, ash value is very important. Okay, so this is the second physical evaluation of the basma. First one is loss on drying at 105 degrees Celsius. Okay, and the third one is solubility. So solubility, the basma is the process is the basma. The obtained basma is dissolved in different solvents to check the percentage of solubility. So based on the basma sample, the solvent will also be different. So in sulfur, after purification, as a purpose of quality control, we used to check the solubility of sulfur in carbon disulfide. So as per the different basmas, different solvents are used for the to check the solubility of basma in different solvents. Okay, so this is the solubility, which is the third in physical evaluation of basma. Next one is specific gravity at 25 degrees Celsius. So this is determined by pycnometer. Pycnometer is nothing but specific gravity bottle. So specific gravity is checked in relation to water. So we check the specific gravity, or it is a relative analysis, relative parameter. That is, we check the specific gravity, or we compare the specific gravity with the specific gravity of water. So since we all know specific gravity of water is 1. So we will compare the specific gravity of the sample to the water. So usually, specific gravity of the basma should be below 1. So that is, this is a very important test, because this is checked in the density, or the specific gravity is analyzed in the process Varitharatva. So in Varitharatva, we know take some quantity of water in a vessel or a glass, and sprinkle the sample, the basma sample or kajali on the water, and observe whether the sample is sinking into the water, or it is just floating over the water. So this is the process of Varyadaratva. So it implies that the produced or the produced basma is having a specific gravity which is less than water. So that is why it is just if it is floating over the water, floating on the water, it implies that the specific gravity of the produced basma is less than that of water. So that is why it is just floating over the water. So we know mercury is having a specific gravity of 13.59. So after preparing kajali, it floats on the water. That means the specific gravity has reduced to less than 1. So that is the importance of Varyataratva, and hence density or specific gravity test is very important in the aspect of asthma. Okay. And next one is pH. pH is a measure of hydrogen ion. We all know that. And the concentration, hydrogen ion concentration. And we know below 7 it is considered as acidic, 7 is considered as neutral, and above 7 is considered as alkaline. And basically basmas will have a range of 7 to 8.3, 8.5. So Naga Basma is having a pH of 7.5 to 8.3, and basically Sudha Vargas will be lie above the 7, because Sudha Vargas are having alkaline property. So that is why it is very effective in acidic acidity and all. So Sudhavarga Drivya, Sudhavarga Basmas will have the pH of above 7. So basically, the basmas will have pH above 7 or above 7. Okay. So this is the determination of pH, and this is the pH determination machine. Okay. So these are the physical evaluation. So we completed physical evaluation. There are like 5 tests are done in the physical evaluation. First one is loss on drying at 105 degrees Celsius, and which is done through weighing balance, desiccator, and a ceramic crucible is needed, all needed for a loss on drying. LOD at 105 degrees Celsius, ash value, solubility in different solvents are checked, specific gravity at 25 degrees Celsius, and pH. These are the physical evaluation of the basma. Next one is chemical evaluation. So coming to chemical evaluation can be classified into 2, that is qualitative as well as quantitative analysis. In quantitative analysis, it is again divided into 3: ash value, gravimetric analysis, volumetric analysis. Qualitative analysis is Namburi's phased spot test, that is NPST, Namburi phased spot test. Okay, so first we will move on to quantitative analysis. So first one is ash value, that we already explained. That is, it indicates it gives an idea of the purity as well as the quality of the prepared sample, and it indicates that why it is also considered in chemical analysis is that it indicates the amount of silica present in the sample. So it is chemically also it is relevant. And gravimetric analysis is that qualitative analysis of a mass of solid. That is, it is usually used to determine the atomic mass. So that is the gravimetric analysis. And volumetric analysis, that is, we are actually familiar with volumetric analysis. It is done by titration analysis, and we have studied this volumetric tests in the +2 level and the chemistry aspect. So we used to do titration for the analysis of specific metals. So each and every metal we will use a volume of solution of non-concentration, which is used to determine the concentration of the analyte. So likewise, different solvents solutions are used to analyze different elements. that is magnesium, manganese, calcium, uh, iron. So these are all identified through volumetric analysis. So these are the three quantitative analytical methods that are done in the chemical analysis. Okay, hash value, gravimetric analysis, volumetric analysis. Next one is qualitative analysis, that is Namburi phased spot test. So whether the prepared plasma is properly prepared or not. For that purpose, we are using Namburi phased spot test. So this is a technique to identify the purity and quality of plasma as well as Sindura. So in this method, the method is actually the Waterman's filter paper number 1 is um, is actually impregnated with the or reacted with the suitable reagent, standard reagent. First, we will take a Waterman's filter paper number 1, and we will invariably impregnate this Waterman's filter paper number 1 with the suitable reagent according to the sample. For each sample, the reagent will be different, and the and after the reagent is incorporated in the Waterman's filter paper 1, it is then again dried, and this dried paper is used for the analysis. So onto the dried paper, we will drop the solution of the sample in solution of the sample, and the observations are done in specific time intervals. So it will look like this. So we will actually drop the solution of the sample into the onto the Waterman's filter paper 1, and we will observe at a specific time interval. So based on the specific time interval, this is having three phases: first phase, second phase, and third phase. First phase is also known as immediate reaction, so which occurs within 5 minutes. And second phase is the delayed reaction, which observes between 5 to 20 minutes. And third phase is the late reaction, which is beyond 20 minutes, that can take up to hours, and it can take up to days to happen a reaction, to observe a reaction. Okay, so these are the three phases of NPSP analysis. First phase is the immediate reaction, which happens within 5 minutes. Second phase is delayed reaction between 5 to 20 minutes. And third phase is late reaction, that is beyond 20 minutes. Okay. So in this picture, this is a Namburi phased spot test of Loha Basma. The sample used for this is 0.25 grams of Loha Basma, and the Waterman's paper is treated with the potassium ferrocyanide. That is 5% potassium ferrocyanide. And the first phase you can see a blue spot. Second phase you can see an expanded blue spot. And in third phase you can actually see a deep blues on the center, and surrounded with or encircled with a light blue surface, light blue circle. And you can also see the serrated blue which encircles the blue spot. And on the outer layer there is a green irregular ring also see. So based on the observations we got on the Waterman's filter paper, we will compare the results with the standards. So there are a set of standards also available. So we will compare the available or observed NPST to the standards. So then we will have the conclusions. Okay. So this is the Namburi phased spot test. So these are the chemical analysis, qualitative as well as quantitative. In qualitative, in quantitative, we covered ash value, gravimetric analysis, volumetric analysis, and in qualitative, we covered Namburi phased spot test. So these are the chemical analysis. We covered physical analysis, organoleptic analysis, physical analysis, chemical analysis. Okay. Now we have instrumental analysis. That is the fourth one, instrumental analysis. This instrumental analysis is again divided into four. That is spectroscopy, X-ray techniques, microscopy, and thermal energy. So this classification is based on the source or the analyzing technique that is used for the determination of an element in the sample. So spectroscopy uses electromagnetic radiation, X-ray uses X-rays, microscopy the determination is done using a microscope, and thermal energy determination of the or reaction of the specific samples to thermal energy is analyzed through thermal energy techniques. So these are the 4 instrumental analysis which are actually very relevant and very widely practiced also in pharmaceutical companies as well as for the research aspects also. These are very important. So first we will move on to spectroscopic analysis. So the spectroscopy, that is basically spectroscopy is related to the interaction of light with matter. So the interaction of light with the substance and the subsequent energy transfer ends with the 3 process, that is absorption, fluorescence, and emission. So the light, which when it is interacted with the matter or the sample or the element, first it is absorbed, then a fluorescence is produced, then based on the element, based on the each element, specific patterns are emitted. So based on the emitted patterns, based on the conclusions drawn out of the emitted patterns, we determine or we conclude or we will get a elemental composition of the sample. So that is the main process, main 3 process which happens when light interact with the matter. Okay, and there are 2 levels of by which the substance can interact with the light. So there is atomic level as well as molecular level. So when the light interact with the matter, first absorb the light rays, then they will produce their own fluorescence and they will emit certain and the fluorescence is produced because of the excited state of the matter. So the ground state is converted into an excited state, and from the excited state, the specific fluorescent rays are emitted. So which is again detected in a detector, and the conclusions are made. The determination is done. A determination of the sample or the composition of the samples are identified through spectroscopy. So the spectroscopy is a technique in which the light rays are used for the analysis of the elements of the sample. Okay. So these are the spectroscopic techniques that are nowadays carried out to determine the elemental composition. Atomic absorption spectroscopy, atomic emission spectroscopy, flame photometry, plasma emission spectroscopy, inductively coupled plasma, ultraviolet visible spectroscopy, fluorometry, molecular fluorescence, Fourier transform infrared spectroscopy, Fourier transform Raman spectroscopy, microwave spectroscopy, nuclear magnetic resonance spectroscopy, electron spin resonance spectroscopy. So in which the important ones, I will explain the important ones here. Okay. So the first one is atomic absorption spectroscopy. So this is a technique which is invariably used for the identification of heavy metals. So when you hear atomic absorption spectroscopy, you need to remember it is for the identification of heavy metals in a given sample. So used for heavy metal identification and quantification. And the peculiarity of atomic absorption spectroscopy is these are very useful tool for determining the concentration of specific mineral in a sample. Specific mineral in a sample. That is, for each sample, you need to. This is the only single element can be identified through one run. So that is the importance of specific mineral in a sample. So if you usually heavy metals and in heavy metal analysis, you will do the analysis for mercury, cadmium, lead, and arsenic. So for each heavy metal analysis, you need to perform a separate AAS, atomic absorption spectroscopy. You need to use specific sample solution for each of the heavy metals. So, but this can be done to determining the concentration of that particular heavy metal in a sample. For that purpose, it is very precise. So, in atomic absorption spectroscopy, AAS uses the electromagnetic radiation in a sample on a sample to determine elemental composition. The wavelength of the energy absorbed or emitted by atoms is characteristic to each element. So by that, analysis is done. This method is very sensitive and enables to detect even small amounts of an element in a sample. That is up to 1 ppm level, parts per million level, we can identify through AAS. So that is a peculiarity of AAS. And in the principle of atomic absorption spectroscopy follows Beer-Lambert law. According to this law, the absorption of a spectra, light spectra, UV spectra, is proportional to the concentration of the metal present in the sample. So, likewise, so in that way, the concentration, how much quantity is a specific mineral is present in the sample, that can be identified through atomic absorption spectroscopy. So that is the one thing that you need to remember when you listen AAS, when you want to identify or determine the heavy metal in a sample, in any sample, that heavy metal should be analyzed. Then you can go for atomic absorption spectroscopy. That is a very precise technology. Okay, the principle. So this is the working principle. This is for BAMS level, this is not required, but in MD level, it is not required for the exams and all, but to know what is happening inside the AAS machine. So, and working principle of the AAS is actually good. So, this is the original AAS machine. Okay. But this is a schematic diagram of flame atomic absorption spectrometer. Okay, so in which you can see a round bottom flask is there, in which a sample solution is taken in that flask, which is connected to capillary tube, and this capillary tube is again connected to spray chamber. Into the spray chamber, the fuel or gas of different combustible gases are given through the to the spray chamber, and there is a burner is there, and you can see the flames there, and after it is being burned, the atoms are the sample is burned, it has to be exposed to UV light rays, so certain light rays, then only we can call this technique as a spectroscopy, right? So, so the hollow cathode lamp is there, and then there is a monochromator is there, photo multiplier is there, which is nothing but detector, and a digital display or a computer, which is attached to digital display or computer. This is the schematic representation of the original machine. So you can see the round bottom flask on the outer on the picture in which the sample is taken, and the capillary tube also. Rest of them are inside the machine. Okay. So the working principle is at first the sample solution is taken in the round bottom flask, and the sample solution will be aspirated into the spray chamber. The spray chamber, in the spray chamber, the spray chamber will be filled with the combustible gases. The liquid sample is aerolized, and that is why oxidant is present there. It has to be aerolized. Then it has to be mixed with the combustible gases such as acetylene or and acetylene and nitrous oxide. And in this mixing is happening in the spray chamber. So we just have to keep the sample solution inside the you just have to take the sample solution in the round bottom flask, and it has to be kept, the capillary tube has to be inserted into the sample solution. That is the only thing that we had to do, and rest of the thing that will machine itself will do the rest of the thing, so rest of the procedure. So as soon as the sample solution is aspirated into the spray chamber, this aerolized sample solution will mix with the fuel gases, combustible gases. So that will actually eventually help to burn the sample. Okay, so after and the burnt in the and the after the burning process, the individual atoms of the samples are released to form a cloud in the flame. So that is why it is known as atomic absorption spectroscopy. So the from the crystals, individual atoms are released. So it is known as atomization. Atomization is happened in the burning process. Burning process, the atoms are released, and these atoms when the atoms are released, it will be in a ground state. So to excite into an high energy state, you have to expose these atoms to a UV light. So for that purpose, it is done by hollow cathode lamp. So on absorbing the UV light at the specific wavelength, at the ground state metal atoms will excited into higher energy state atoms. And then the region of the spectrum to be measured is selected by the monochromator. The isolated spectral lines falls on the photomultiplier. That is, the isolated spectral lines are falls on the photomultiplier or the detector. And the output is amplified and sent to a readout device or a digital or analog through a computer data processing system. And the data is processed through software. So this is the process of atomic absorption spectroscopy. So first, the sample solution is kept in the round bottom flask. It is through the capillary tube, it is aspirated into the spray chamber. There it is aerolized and it is mixed with the fuel gas or combustible gases like acetylene, and burning occurs. Through the burning, when the sample is burned, the atoms of the crystals are freed. Then these atoms are excited to a higher energy state by hollow cathode lamp. Then it is identified in monochromator, detected in photomultiplier or detector, and which is then displayed. Which is then the output is then identified or analyzed by the computer software. So then we will get a result. Okay, this is the process of AAS. So on simple in simple language, we can actually say a light source, that is a hollow cathode lamp, atomizer, monochromator, and detector. This is the four principles that is happening in AAS, atomic absorption spectroscopy. So it is an absorption spectroscopy. The light are absorbed and the elements are converted from a ground state into a higher energy state. Okay, this is the machine, and this atomic absorption spectroscopy is widely used in environmental chemistry, geology, soil science, mining and metallurgy, food sciences and medicine, and helps in quantitative determination. And determination usually up to the trace elements we can identify through AAS. Up to parts per million, 0.1 to 100 parts per million trace elements, that elements can be identified through AAS. But only mono element, single element can be identified in one run. That is the important thing. Okay. So AAS is done to identify the heavy metals in a given sample. So this is also used for the heavy metal analysis of medicines, DESA medicines. since we have all the heavy metals in the acids like mercury, lead, cadmium, and arsenic. So we need to do AAS for the identification of heavy metals in a sample. Okay. Next is atomic emission spectroscopy. So this is the method of chemical analysis that uses the intensity of light emitted from a flame, plasma, spark at a particular wavelength to determine the quantity of an element in a sample. So this is also used for the quantification of the element in a sample. And the wavelength of the atomic spectral line in the emission spectrum gives the identity of the material, and the intensity of the emitted light is proportional to the number of atoms. So we can actually identify the elements in a sample, identify the elements in a sample, as well as we can identify the concentration of that particular sample in that particular element in a sample. So for the purpose of identification as well as the concept to determine the concentration of the element. For both purposes, atomic emission spectroscopy can be used. The sample in the peculiarity of atomic emission spectroscopy, as it is mentioned here, the light emitted from a flame, plasma, spark. That is the sample, the basic theory behind the spectroscopy is the ground level atoms has to be excited, converted into an excited state, then only there will be an energy, a spectra can be formed, can be obtained. So the sample may be excited by various methods. So the first one is flame. So that is what happened in AAS, that is atomic absorption spectroscopy, that is flame spectroscopy, which uses flame for atomization. And next one is inductively coupled plasma. So for that purpose, we are going to learn about inductive coupled plasma, AES, in the next slide. So AES generally used for the identification as well as quantification of an element in a sample. Okay. Inductive coupled plasma atomic emission spectroscopy, ICP AES. It is an analytical technique used to determine how much of a certain element are present in a sample. The fundamental property of this process is that each element emits a specific energy at specific wavelength, which is peculiar to that atomic character, which is peculiar to that crystal. Okay. So this is also used for the identification of heavy metals. But the difference between AAS and ICP is that the detection limit is more in ICP, and and multi-elemental analysis can be done in ICP. But in AAS, we can only analyze or determine one element at a time. But in ICP, we can analyze, we can determine multi elements in a single time. So, and the detection limits are also very vast in inductive coupled plasma. Like the elements including arsenic, lead, selenium, sulfur have detection limits of a few parts per billion. That is 1, 2, 3. That is a few parts per billion. Up to few parts per billion can be billion can be identified. ppb can be identified for arsenic, lead, lead and selenium, sulfur. And for fluorine, chlorine, bromine, the detection limit is hundreds of ppb. And the noble gas elements, the neon, oxygen, and hydrogen, which is having a lower molecular weight, are not able to identify, are not able to measure through ICP. So that is the only disadvantage. That is the one disadvantage. And coming to the advantages and disadvantages in detail, the first one is excellent limit of detection. That is, I already explained to you, it is parts per billion. In the AAS, it is parts per million. We can only see up to parts per million limit. If the element is present in a particular sample in parts per billion quantity, we will have to go for ICP. And multi-element capability, that is the second important one. And stable and reproducible signal. So the same process can be reproduced and we will get the same results. Okay. And the main disadvantage is that cost and operating expenses. Netty-coupled plasma is very expensive procedure than the atomic absorption spectroscopy. AAS itself is an costly procedure. That is, for a single sample, we need to pay like 500, 300 to 500 is the range for price range for AAS. But ICP it is above 1000, I think. So for a so it is very costly and operating expenses are more. And the samples typically must be in a liquid state. So that is the second disadvantage. Okay. And there are also several other variants of ICP and the application, coming to the application of ICP. These are the several applications of ICP. Quantitative determination of metals in a solution. Qualitative determination is also possible as each element emits its own characteristic line spectrum. Okay, qualitative can be, analysis can be done. Precious metal and estimation at low level, heavy metal estimation at sub ppm level, rock, soil, fly ash. The complete analysis of all these things can be done in ICP. Environmental samples analysis, air, water, soil, sediments, and biological sample analysis, polymer industries, pharmaceutical industries. So these are the several areas that ICP can be applied. ICP analysis can be applied. Okay. And there are several other variants also for the ICP. Few of them are inductively coupled plasma mass spectroscopy, which are used in the isotope and radio studies, and which are having high precision. And inductively coupled plasma optical emission spectroscopy, which is a very high-end analysis, in which 60 elements can be identified or determined in single run, that too within 1 minute of the time. So within 1 minute, we can analyze the sample in optical emission spectroscopy, that is OES, ICP OES. So these are the variants of ICP. So ICP and AAS are the same, more or less same techniques, in which the heavy metals can be identified in a sample. But in ICP, the detection limit is more than AAS, and multi-elemental analysis determination can be done in ICP. So these are the advantages of ICP over AAS, and disadvantage is costly. It is very costly. Okay. So these are the things with the ICP. That's the ICP. So ICP, this is the machine of ICP, inductively coupled plasma atomic emission spectroscopy. This is the AES machine. And next one is plasma emission spectroscopy. For it is used for qualitative as well as the quantitative analysis of metal and non-metal, even at trace levels. So this is plasma emission spectroscopy. Okay. Next one is ultraviolet visible spectroscopy. So in the UV spectroscopy is a type of absorption spectroscopy in which light of ultraviolet region, that is which ranges from 200 nanometer to 400 nanometer, is absorbed by the sample molecule, which results in the excitation of the electrons in the sample from ground state into an energy state. And the absorption and the excitation results in the production of distinctive spectrum, which aids in the identification of the compound. So here the difference is they are using ultraviolet rays, which ranges from 200 nanometer to 400 nanometer for the purpose of identification of elements in a sample. So the use is provides valuable information through absorption spectrum, and used in identification and structural analysis of organic compounds. So organic compounds, in organic compounds, the elements or the composition of the organic compounds can be identified through ultraviolet visible spectroscopy, in which the source of light is ultraviolet light. It is having a 200 to 400 nm range. Okay, so this is the only difference. So this is also used for the identification and structural analysis of organic compounds. This is the ultraviolet visible spectrometer. Next one is Fourier transform infrared spectroscopy, which is also known as FTIR, and which is the it is considered to be one of the most effective technique to study and understand the chemical and surface chemistry in various types of membranes. So chemical and surface chemistry. So in FTIR, what happens is it is also for the purpose of analysis of chemical composition and surface chemistry also can be identified in FTIR. And this is the process of FTIR, in which it is an absorption spectroscopy technique. That is the main, you can, from the term, that is Fourier transform infrared spectroscopy, we can detect that infrared rays are used for the excitation of the molecules. So these are the simple things that may, that is different from the other techniques. In AAS, it is UV and flame, and in ICP, it is electromagnetic radiations, and in UV visible spectroscopy, it is UV rays. So these are the things that are different from ICP. It is plasma, not UV, not electromagnetic. It is plasma. I inductively coupled plasma is used for the excitation of the atom. So in Fourier transform infrared spectroscopy, that is FTIR, it is infrared rays are used for the excitation of the sample. Okay, so when it is absorbed, when the infrared rays are when the sample absorbs the infrared rays, some of the infrared rays are passed through the sample, and some wavelength may be absorbed while other merely pass through unaffected. And a specific molecule, based on that, the a pattern is detected in the computer. So likewise, we can identify, determine the elemental composition of a sample. So it is absorption spectroscopy. The light is absorbed and a specific pattern is produced as per the element in the sample. So the pattern will differ based on the element in the sample. Okay. So this is used for the specific uses are the identification and structural analysis of organic compound, natural polymer, functional group of a given organic compound can be identified, and it is highly effective in identifying unknown solids and liquids of various pigmentations, including industrial dyes, pigments, and oils. So unknown oils or pigments, dyes can be identified by FTIR. So if in the pharmaceutical point of view, it is very necessary for the for the analysis of specific use of dyes in a medicine. So if it is not the approved dye is used in the specific pharmaceutical technique, pharmaceutical compound, we can detect that in FTIR. So what kind of dye is used, how much it is used, all these can be identified through FTIR spectroscopy. Okay. And next one is so FTIR spectroscopy is ideal for fluorescent samples also. So these are the uses of applications of FTIR. Okay. This is the machine of FTIR. Next is the Fourier transform Raman spectroscopy. So in this, a single wavelength laser is focused on a sample. So the laser excites the bonds of the molecule, then generates measurable scattered light to identify the material in a sample. So the Fourier transform infrared spectroscopy, that is absorption spectroscopy. That is absorption of light occurs. But here scattered light is scattered and produced the pattern, and the pattern is produced, then the pattern is analyzed and identified or determine the elements in the sample or composition of element in a sample. So in which a single wavelength laser is focused on a sample, the laser excites the bonds of the molecule and then it generates a measurable scattered light to identify the material in a sample. And this is the process, and this is effective. This is an highly effective method for reliable identification of an unknown substance. So unknown substance can be identified through Raman spectroscopy. And Raman spectroscopy is best when it is used for the analysis of substances which are contained in sealed containers. So in sealed containers, which are sealed containers means the containers which are transparent or translucent containers, we can identify the material which is if you don't know a material which is contained in a sealed container, we can actually, if it is a translucent or transparent, transparent or transparent material container, we can analyze the elemental composition of the, we can analyze the material itself without even coming direct contact with the material. So this eliminates the need for direct contact with potentially hazardous unknown substances. So for that purpose, Raman spectroscopy is very good, very precise. So to analyze the substances contained in a sealed containers, FTRS is very necessary. And identification of potentially threatening materials in aqueous solutions can also be identified through Raman spectroscopy, and excels at identification of white and light powders. So these are the important aspects of the important uses of Raman spectroscopy. Okay, so this is the process of Raman spectroscopy, and this is the machine of Raman spectroscopy. Okay. Next one is nuclear magnetic resonance spectroscopy. So this is the machine of nuclear magnetic resonance spectroscopy. This is for the identification of identification as well as structural analysis of organic compounds. So nuclear magnetic resonance spectroscopy is used for the identification and structural analysis of organic compounds, and it is a tool for the identification of the position of the functional groups also. So this is mainly used for the organic compounds. Okay. So this is the last one in the spectroscopy. Next one is X-ray. So in spectroscopy, we have covered atomic absorption spectroscopy, ICP, plasma emission spectroscopy, then Fourier transform infrared spectroscopy, and as well as Raman spectroscopy, and the last one is nuclear magnetic resonance spectroscopy. So these are the spectroscopic analysis or spectroscopic tests which are performed for the analysis of a prepared plasma sample. Okay. So through these spectroscopic techniques, we can determine the composition of a specific mineral or metal, as well as the concentration also can be identified. But find out or to determine the character or the characteristic changes that has happened in the atomic level or that has happened in a crystal that can be determined only through X-ray diffraction techniques. So here comes the X-ray techniques. So and ICP also can be used for the analysis of structural chemical structure can also be identified through ICP, but the X-ray techniques, which include X-ray diffraction as well as X-ray fluorescence spectrometry, or simply it can be explained as XRD and XRF. So these are the techniques which would explain the structural differences of a same metal before and after purification. So first one is X-ray diffraction. So we know it is a powerful non-destructive technique for characterizing crystalline minerals. So it will identify the crystalline minerals, but it will characterize the minerals also. So how much it is differ from the raw material. So these can be identified through X-ray diffraction. So the basic principle of X-ray diffraction is, so there is an incident beam. You can see that there is an incident beam. The sample is kept in the middle, and when an X-ray, so as the term indicates, here for the analysis purpose, we use X-ray. Okay, so when a beam of X-ray illuminate or irradiate a single crystal, it diffract and many spots are produced. The position of the spots and the intensities of the spots are determined by the nature of the crystal which is analyzed or nature of the sample. Okay, so how wave reveal the atomic structure of the crystals. How an X-ray wave reveal the atomic structure of the crystals are studied in X-ray diffraction. So an incident beam is illuminated the sample, and the sample then diffract the beam at a specific angle and produce several spots, and the intensity of the spots, the position of the spots based on differs with each element. So through that we can identify the element and the nature of the element also. In sulfur, we are having several isomers of sulfur. So whether it is monoclinic sulfur, whether it is rhombic sulfur, these differences can be identified in X-ray diffraction. In other techniques, we can only know the concentration as well as the element. We can know that sulfur is present and sulfur is present in this quantity, this percentage. But we cannot explain, we cannot get an idea of which type of sulfur is present in the material. So through X-ray diffraction, we can analyze the specific structural differences in a crystal. Okay. So this is the basic principle of X-ray diffraction. This X-ray diffraction is based on the Bragg's law, which is n lambda is equal to 2d sine theta. And at the end of the process, we will get a chart like this, based on the peak of the intensities and based on the peak of the wavelength and intensities and position of the spots. We can identify the element and its nature also, whether it is crystalline, whether it is amorphous. All these things can be identified in X-ray diffraction. It is a very important thing as far as when it is concerned with the plasma or shodhana, because we can actually determine the elemental composition through many other processes, but only the X-ray diffraction and SEM, like scanning electron microscopy, which we will learn later. Only through that things we can explain the actual difference that is happening, actual difference in a atomic um, uh, atomic level that is happening after a Shodhana or Marana process. So for that purpose, X-ray diffraction is very essential. So this is the sample of the result of X-ray diffraction, and this is an X-ray diffraction machinery, and the left one is a desktop model of X-ray diffraction, and the right one is the original model of X-ray diffraction. So why XRD is considered as important? So to find out the crystal structure of an unknown material. So, so till now we have discussed about the elemental composition and the concentration of elemental composition. So from XRD we can know about the crystal structure of an unknown material, and to study the nature of the crystalline substances, phase identification of crystalline substances, compound of a material or free metals can also be detected, and measure the average spacing between the layers of the rows of atom, and determine the orientation of single crystal or grain, measure the size, shape, internal stress of a small crystalline regions, atomic spacing study and information on unit cell dimension, and provides vital information regarding the arrangement of the atoms. Okay, so this is why we consider XRD as a high-end analytical parameter, analytical test for the analysis of BUSMA. Applications of XRD. XRD is a non-destructive technique to identify crystalline phases and orientation, to determine structural properties, to measure thickness of thin films and multi-layers, to determine atomic arrangement, powerful and rapid detection. Within 20 minutes, we will get the results. And detection limit 3% in two-phase mixture. So up to 3% we will get that we can detect the elements in a sample. And in as far as this is a general applications, as far as in Bhasma Parisha, it is to find out the structural differences that has happened before and after each process. So for that purpose, we can do XRD, X-ray diffraction. Next is the X-ray fluorescence spectrometry, that is XRF. So in XRF, an X-ray source is used to, like the XRD. So in XRD, after the sample is being illuminated or irradiated with the X-ray, it diffracted in a specific pattern. And in X-ray X-ray fluorescence, it actually emits fluorescence. That fluorescence or a color will depend upon the element in a sample. So an X-ray source is used to irradiate the specimen, and the specimen then causes the elements in the specimen to emit their emit or fluorescence their characteristic X-rays. So there will be a detection system, that is a computer, which measures the elements and their amounts. So XRF is a multi-elemental analysis can be done through XRF. So this is the X-ray fluorescence, XRF, X-ray source. Through the X-ray source, X-rays are irradiated the sample, and the sample, the material, based on the material or the element in the sample, based on based on each sample or each material, the fluorescence pattern is also differs. So based on that, different type of fluorescence is emitted, and it is detected and evaluated through a computer. So this is the X-ray fluorescence. So this is the procedure I just explained to you. Then is the X-ray. This is the X-ray fluorescence chart, which is obtained after the after the computer measurement, computer analysis. So based on the intensities, based on the peaks, several peaks, we can identify the elemental composition in a sample. So this is also used for the elemental identification of elemental composition in a sample. Only the XRD used for the structural analysis. Okay, so in XRF, the peaks are used for the identification of the elements. Okay, next is the application of XRF. So XRF is also a non-destructive technique used for chemical analysis of material to find out the elemental composition which is suitable for solid, liquid or powder samples, and qualitative analysis as well as quantitative analysis can be done. So in which in XRF an unknown material can be tested. So in which the material is identified. So that part can be considered as a qualitative, and we will also get the percentage of the element present in the sample. So in that way, we can say it as a quantitative measurement. Okay. Next one is so in the XRF is done through two methods, that is energy dispersion method and wavelength dispersion method. The energy dispersion, that is EDXRF, is a very fast qualitative elemental analysis, which is elements from sodium to uranium can be detected simultaneously and obtained in within minutes or seconds. So the elements will be detected in a in their oxide form. That is, in XRF analysis, we will get SO2 or sulfur. So in an oxide form, we will get the result. Okay. So by that, we can identify the elements which are ranges from sodium to uranium. Okay. And wavelength dispersion, that is lambda dispersion, that is which is used for the quantitative technique. The peak height for any element is directly related to the concentration of that element in the particular sample. So this is used for the solid one. EDXRF is generally used for the powder samples, and wavelength dispersion is used for the solid samples. Okay. Next one is XRF applications. So in which you can see that in it is XRF is can be applied in the metals and alloy and environmental aspects, that is geology, soil surveys, field analysis, and examine everything from sewage, sludge, car exhaust, river water, and so much more. Like in car exhaust and all, they will identify the elements that are present that emits from the car exhaust. So we will get a full elements that are present in a sample from sodium to uranium. That is the main advantage of XRF. And medicine is high level of certain chemicals which are present in the body can be identified through XRF. So these are like two type of XRF machines are available. That is X-ray fluorescence spectroscopy, the laboratory machine, as well as a handheld XRF machine is also available. So these are these are the applications and principle of XRF. Next is X-ray photoemission spectrometry, that is which is mainly used for surface analysis. Qualitative identification of the elements in a sample can be done through X-ray photoemission spectrometry, useful in determining the valence state of the atoms present in various moieties in a sample. So various contents in a sample. So so qualitative analysis of a sample can be done through X-ray photoemission spectrometry. Okay. Why it is known as qualitative analysis? Because the surface chemistry can be analyzed through this process. So this is the machine used for the X-ray photoemission spectrometry. And next we will move on to microscopy techniques. In microscopy techniques, we have three different microscopy techniques for the analysis of plasma. That is, first one is scanning electron microscopy, which is also known as SEM, S-E-M. Transmission electron microscopy, which is also known as TEM. And scanning probe microscopy, that is SPM. And electron microscopy. So we know that microscope generally divided into two, that is optical microscopy and scanning electron microscopy. So the optical microscopy is the oldest one. So there are several differences between optical microscope and scanning electron microscope. The first one is main principle of work. So the main principle of work in optical microscope is the light. We use light to examine the sample. But in scanning electron microscopy, as the term indicates, it is electron emission is used for the analysis or observation of the sample. And coming to the next main difference between OM and SEM, the magnification of a OM reaches to the ranges between 400 to 1000 times of the original size. And so a sample can be magnified to 1000 times in OM, optical microscope. But look at the SEM, that is 3 lakh times um, can be amplified and it can be observed through the SEM. So these are the main difference of OM and SEM. Okay. And this is an effective method in analysis of organic and inorganic materials on a nanometer to micrometer scale. Energy dispersive X-ray spectroscopy, that is EDS, works together with the scanning electron microscopy to provide qualitative and semi-quantitative results. So it is basically a qualitative analysis. That is, scanning electron microscopy is done to detect the surface morphology of all kinds of material. So this is also very important when it comes to VASMA analysis. So the surface morphology drastically differs when it after being subjected to Shodhana or a Marana. So for the purpose of identification or the analysis, the surface morphology, whether it is changed or not, whether the surface morphology is remains the same, we can do the SEM. So to detect the surface morphology of all kinds of material, you can do scanning electron microscopy and helps to detect the particle size. And it also applied to surface related physical properties such as topography, depth profiling studies are also, in that aspects also scanning electron microscopy is very useful. So as far as Basma Pariksha concerned, surface morphology can be identified through scanning electron microscopy, SEM. So you need to remember that thing, surface morphology can be identified through SEM. When you hear XRD, you have to identify the character. Then structural changes can be identified through XRD. Characterization of a crystal can be done through XRD. And XRF is unknown minerals from sodium to uranium can be identified through XRF. So you just have to give your sample to the XRF. You will get whatever elements are present in that element sample. You will get a list in a percentage level. So in a percentage. So that is all these process, you don't have to go for the principle and all. You have to know why it is used and what is the basic principle. In like we have explained, like in X-ray diffraction, X-rays are used. So that is common sense, right? So in that aspect, you have in that aspects you need to learn, and also the main purpose of that um, test. In STEM, it is surface morphology of all the materials. Okay. In this is the scanning electron microscope. Okay. Next is the transmission electron microscopy, that is TEM. So TEM or conventional, it is also known as conventional transmission electron microscopy, that is CTEM. Max Knoll and Ernst Ruska invented TEM in 1933 in Berlin. The main uses are, this technique is utilized for analyzing surface structure, that is morphology, surface imperfections like defects, Crystal structure of an atom. Surface imperfections can be utilized for the test of precious stones. Okay, crystal structure of the atom, size of the particle, samples composition. So these are to identify, to determine these aspects like size of the particle, sample composition, crystal structure. TEM can be used. And this is used to study the structure, morphology, cross-section and crystallization of metallic alloys and microstructure of composite materials. So TEM is a transmission electron microscopy. And the main principle is that an electron beam is passed through a sample, which rendering its interaction with the sample. As a result, an image is produced. Okay, an electron beam is passed through the sample, and after interacting with the elements in the sample, a image is produced. This image can be magnified and focused on the device used for imaging, like a fluorescent screen on a photographic film layer. So after we analyze the magnifies and analyze the image, the result, elemental composition, elemental structural nature of the structure of the element can be determined through transmission electron microscopy. So this is the machine that is used for TEM. And the next one is scanning probe microscopy. So that is the machine you can see in the right side. This is more or less similar than like to a optical microscope, which is widely used for surface studies on nanoscale range. And it is used for helps in the characterization of the surface structure and helps in the measuring the hardness of the materials also. So these are the things which are comes under the microscopy. Okay. And in the STM, the definition of STM, the full form of STM is a scanning tunneling microscope, and AFM is atomic force microscope. So the scanning probe microscopy is widely used for the surface studies to analyze the surface of a material. So there are certain variants of the scanning probe microscopy, that is STM and AFM. STM is a scanning tunneling microscope and AFM is atomic force microscope. So you just need to be familiar with the terms. Okay. So STM helps in the scanning tunneling microscopy helps in the characterization of the surface structure, and AFM helps in the measuring the hardness of the material. So these are the variants of the scanning probe microscope. Okay. Next is a thermal energy. So that is the last one in the instrumental analysis. First one is spectroscopy. Second one is X-ray techniques. Third one is microscopy. And fourth one is thermal energy. So the thermal energy, which is again divided into three aspects, that is thermomechanical analysis, differential thermal analysis, thermogravimetric analysis. In thermomechanical analysis, I will only explain the uses of all these thermal analysis, because we don't actually do by actually perform these analytical methods as we do the other analytical methods. So that is why I will only explain the uses of this thermal energy analysis. So in thermomechanical analysis, we can, this is the machine of the thermomechanical analysis, and which helps to detect the characterization of the composite and laminate materials. Okay. And gives the valuable information about samples' mechanical properties. That is a thermomechanical analysis. Okay. This is the thermomechanical analysis machine. Next one is differential thermal analysis. through which endothermic as well as exothermic behavior of a particular sample at high temperature can be identified. And analyzing the characterizing clay material, analyzing and characterizing the clay material, ceramic and ores. These can be identified through thermal analysis, differential thermal analysis. Okay. So endothermic as well as exothermic behavior of a particular sample can be identified through differential thermal analysis. Next one is thermogravimetric analysis. So in which the principle is the weight of the sample is measured while the sample is heated at a constant rate. So so weight of the sample. So the quantitative analysis of thermal reaction like mass change. So the mass change, evaporation, decomposition, gas absorption, dehydration. In all these circumstances, the sample weight is measured while the sample is heated at a constant rate. So to identify quantitative analysis of thermal reactions like mass change and evaporation, decomposition can be identified through thermogravimetric analysis. So these are the analytical aspects of BASMA. Okay. So there are traditional as well as to conclude the session. I will just go through the. I know this is a little bit of boring subject because we have to learn about new instruments. We have to learn about new terminologies, which we are not being familiar with that much. So this will be slightly difficult to memorize and all. So for that purpose, I will just go through the slides to uh, tell you about the important aspects that you need to memorize when you go through the process. So just from the first one, I have told you that there are two type of analytical tests are performed as a part of BASMA Pariksha for the purpose of quality control analysis. That is, one is traditional analytical test and current analytical test. Traditional analytical test is nothing but the BASMA Parikshas, which is explained in detail. Okay. So BASMA Parikshas are also divided into two, that is physical and chemical analysis. These aspects you need to learn every aspect of BASMA Pariksha. There is no doubt in that. So traditional aspects, you need to learn about the BASMA Parikshas, each and every BASMA Parikshas, physical test, chemical test, everything. The current analytical test is again divided into organoleptic evaluation, physical, chemical, and instrumental. In organoleptic evaluation, there are four um, factors are analyzed: color, odor, taste, and touch. Color is, we have learned the different types of color in BASMA Parikshas, and odor, taste, and touch. These are the organoleptic evaluation you need to be analyzed after the BASMA being prepared. And next one is physical evaluation. Physical evaluation, loss on rain, LOD is analyzed, ash value is analyzed, solubility uh, uh, in different solvents, and specific gravity. It is very important and which can be correlated to Varidaratva in the traditional process, traditional tests, and pH. So these are the physical evaluation. So we covered organoleptic evaluation and physical evaluation. Then next one is the chemical evaluation. Chemical analysis we actually don't do nowadays because only the ash value we will do for every samples, and Namburi phase spot test. But the two of them, that is gravimetric and volumetric analysis, we will not go for those tests since we will get the uh, uh, volumetric analysis. That is how much amount of element is present in that sample, that composition of the element in a sample can be identified through other methods like XRF and all. So, in chemical analysis, ash value and Namburi phased spot test will only be carried out. So, ash value is for the identification of the quality and purity of the sample, and amount of silica present in the sample can be identified. And Namburi phased spot test is also used for the identity purity of the sample, and resultant Namburi spot is the resultant spot of the test sample is compared with the standard of the NPST. So this is the process of Nambooiri based spot test, and which is being observed in three time frame: first phase, second phase, and third phase. First phase will the reaction which occurs within 5 minutes is considered as first phase, and reactions which occurs within 20 minutes is considered as second phase, and reactions which is observed after 20 minutes and within a certain days is considered as third phase. So that is the NPST analysis, and instrumental analysis is again divided into four, that is spectroscopy, X-ray, microscopy, and thermal energy. These are differ with the method by which the element or the crystal is excited. So spectroscopy, we have learned about atomic absorption spectroscopy. So when you hear atomic absorption spectroscopy, you need to memorize that it is used for the identification of heavy metals in a sample. It is used for the identification of heavy metals in a sample. So it is a specific test for a specific heavy metal. So only a single element can be identified through AAS in one run, and trace elements up to 0.1 to 100 ppm level can be identified through AAS. So working principle, that is not so much important for the BAMS level, but you have to learn in the MD level when you have to do for the dissertation. Okay, and this is the machine of AAS, and atomic emission spectroscopy we have learned, and in which ICP and AAS are more or less similar, but the composition. So, and the plasma is used for the excitation of the material, and disadvantage is cost is the main disadvantage. And next one is we studied plasma emission spectroscopy and ultraviolet visible spectroscopy, and FTIR, this Fourier transform infrared spectroscopy, as well as Fourier transform infrared Raman spectroscopy. These two are very important. Okay. So this is an effective technique to study the chemical nature and surface chemistry of a element. So and in FTIR it is infrared spectroscopy. It is the absorption spectroscopy. But in Raman spectroscopy, it is scattered. Light energy is scattered, and that emitted scattered pattern is studied. So it is highly effective for the identification of unknown substance, and substances which is contained in a particular container.